Swayam Prabha. Digital India. Educated India.
Another very common type of element which finds its usage in mechanical systems and machines are shafts. So we will take up now the oscillation of this very common type of element. We will consider, of course, a perfectly circular shaft of some length and uniform cross section. So this is the uniform circular shaft in question, and the mode of oscillation, as I have already explained in my previous presentation, that it will be about an axis we call the longitudinal axis x, whose origin is here at O. So, if we consider an element we will again consider an element at a distance x from the origin, and whose length or thickness is dx. So, if we imagine this element of infinitesimally small thickness, so the displacements will be that if you take the plane which is at a distance x, this rotation, now the displacement will not be linear displacement but angular rotation. Let this be theta, which will be a function of x and time. As we found in case of a bar, it was u, that is the longitudinal displacement, which was also a function of its position and also the instant we are considering. And obviously the rotation of the other one will be the amount of rotation of this plus the slight difference So these are the displacements of the two ends of the element. Now let us draw the elements separately. This is the element. Now you all, if you consider the motion of this element and find out the equation of motion, which is valid for all such elements at all possible positions. Now here we know that the total moment which will be acting, moment which will be resisting the rotation of this from this side is say m, and the moment which will be trying to so there will be two moments facing, one on this face, because of the twist like this face will be subjected to a resisting moment and this face will be subjected to a moment in the positive twist direction like theta. So therefore, we can say this is a shaft of length dx and say, of course, we have not mentioned the size. Let us consider the radius to be r. Then the twist which this shaft is subjected to, it may be element, but nevertheless it is a shaft, will satisfy our standard relation moment on a shaft by the polar second moment of area is equal to shear modulus G. Amount of twist we know, amount of twist is phi and the length is L. This is the standard relation we know for the torsion of a shaft. The length is L. So, if we now compare this with the standard formula, the moment on this face is m and this face is also m, it is slightly different value. So, m will be m. Second moment of area of a circle with radius r is half or pi G is the shear modulus. What is the amount of twist? Now, this end has moved by theta and this end has moved by theta plus something. So, the amount of twist of this elemental shaft is nothing but that extra something. Otherwise, it is having a rigid body rotation like theta and then an extra amount. So, this is the amount of twist. So, that will take the place of phi. This is the amount of twist and the length of the element of shaft here is nothing but dx, or we get 2m by pi r to the power 4 equal to or from this we get m is equal to pi r to the power 4 by 2 into G So, this is what we find, the expression of the twisting moment in terms of the displacement and the material properties and the size of the shaft, that is R. Next, again we do the same thing, that to find out the dynamics of this element, what is the total moment acting on this? Total moment acting on this is a resisting moment m and a forward moment m plus something. So, therefore, this is the total moment acting on the element in the forward direction, that is theta positive direction. And therefore, this must be equal to Newton's second law, this is the total moment, must be equal to moment of inertia of this element into the angular acceleration. Moment of inertia will be how much? For this we know it will be half mass of this element, that is volume of the element is this, into rho, that is the mass of the element, into r square, This is the polar moment of inertia of the element into angular acceleration. Now what will be angular acceleration? The amount of rotation is given by theta. So d theta dt, del theta del t will be velocity, and del 2 theta del t2 will be the angular acceleration. So from this we get dx cancel, so pi r to the power 4 rho by 2 Now m is this. Using this m and substituting it here, we get del m del x will be equal to g del 2 theta del x2 into pi r to the power 4 by 2 is equal to pi r to the power 4 by 2 rho, or finally we get an equation which is identical in form with the equation of motion for longitudinal oscillation of a bar. This is the equation of motion which is valid, or that is the relationship between the angular rotation, time, material properties, location, and so on. So this, if you remember the previous one, in case of longitudinal oscillation it was exactly same, only here it was E by rho. So the velocity of propagation of torsional wave is given by, and the equation is so this is the velocity of propagation of a torsional wave. Now since the form of the equation is exactly same as the previous one, so for normal mode oscillation now let us consider for normal mode oscillation, all the elements will execute harmonic oscillation of same frequency, and therefore theta xt can be written as a product, a function of x only into a harmonic function of time, which can be cosine omega t or sine omega t. And if we substitute this here, we get so when you substitute this theta here and cosine omega t gets cancelled, so this is the equation we get, and the general solution will be Now, as before, omega can be found out from the boundary conditions of the shaft which are given. So the solutions will be very similar. That means both ends free, one end free, one end fixed, one end free, or both ends fixed. We will get similar kinds of things. So, for example, here also we will find boundary conditions can be of two types. That free means no torque or no moment acting there, and as you know, moment is proportional to the theta dx. Forget about the cosine omega t, and if that has to be 0 all the time, so it means it is same as and for fixed end, twist itself will be equal to 0 for all time. And in case something else is attached, a disc, then the inertia force of that disc is the total moment acting at that end. So similarly, we can proceed to solve various kinds of solutions, and we will get exactly similar expressions, only here that C will be replaced by Ct, whose value is equal to square root of g by rho. In case of longitudinal wave propagation, it was E by rho square root of. So we will not repeat that. Rather, I think we would like to solve an example. So one can easily solve various types of conditions. Free, fixed, free, and fixed, and a shaft carrying a disc at the end. The mode shapes will be also similar to what we got in case of longitudinal vibration of bar for the same condition, same form of solution. Only capital X will be replaced by capital theta, and C will be replaced by theta. So instead of solving the type of problems which we will be identical in form with the problems which we solve for longitudinal oscillation of bar, let us consider a case where we have to deal with the other kind of problem. That means a shaft carrying a disc at the free end. Say the polar moment of inertia of the disc is J0. The length of the shaft is L. So now here the boundary conditions will be what? We have to find out the natural frequency of this, and of course here the material density is rho, shear modulus is G. The boundary conditions we find that if we consider this to be the x-axis and that is origin, and at x is equal to 0, theta x equal to 0, because it is a fixed end. At x equal to L, the moment which is acting on this will be equal to the inertia loading. Now, inertia force or inertia moment acting or torque acting on this will be minus J0 into theta 2 dot. Theta 2 dot at x equal to now, if we know that theta, which is a function of x and t, written for natural mode of oscillation like this, then theta 2 dot is nothing but minus omega square so we can substitute it there and find out the value. So, the moment which is acting here, moment also will be dynamic moment, moment will be the magnitude of the moment because it is also a harmonic function of time into cosine omega t. So, magnitude of the moment at this free end when you are dealing with only magnitude, then it will be minus omega square, sorry, minus J0 into minus omega square theta x. So, you can say when you are dealing with only the magnitude, this x magnitude will be equal to omega square J0 we have to keep in mind that here of course only the magnitude we have to see. Now, we have already seen that theta x we get as C1 cosine omega by Ct x plus C2 this is the form of the solution. So, we know we differentiate once with respect to x and we get d theta x dx. Now, if we use the boundary conditions like say theta is equal to theta x equal to 0 at x is equal to 0, if we put x is equal to 0, this term is 0, here it is only C1. So, this is 0. That means this will give us and therefore, we will have theta x as simply C2 sine in this form. C1 is 0. Now, let us find out moment at x is equal to L. How do you find out moment? Moment we find out magnitude of moment at x equal to L will be equal to we have already seen the expression for moment which was pi r to the power 4 by 2 g d theta dx. So, therefore, moment at x is equal to L will be the same thing when we calculate this at this. So, therefore, this is nothing but now C1 is 0. So, d theta dx C2 if you put x is equal to L here, what we get is and this we have found out already, which is equal to J0 omega square and theta L will be nothing but J0 omega square. Theta at L will be nothing but T2 sine so therefore we get now an equation in this form, which I think C2 will cancel and it can be written in this form. Or we will get omega L by Pt here now Ct we have already found out. Ct was Ct square equal to G by rho. So if you use it here, we get now how much is this? This will be half pi r square into L square G by rho should go. Now this is pi r square is the cross sectional area, L is the total length of the shaft. So this is nothing but the total volume of the shaft into rho. This is the total mass of the circular shaft, and half into mass of the shaft into r square is nothing but second moment of area of the shaft. That means if we treat the shaft as a rotor, then there is a moment of area, polar moment of area. So therefore, the equation finally we get some beta into tan beta there will be 1 J0 here. So it will be equal to so this thus we get a transcendental equation and these transcendental equations can be solved only by computational technique, or in the earlier days it used to be solved by using standard tables. One standard book of table is by Dhanke and Emde. Anyhow, what we will do here, we will give the solutions, first three solutions. First three solutions, of course, in this case will require the two values here. So we don't have it here, we have not prescribed. So if you want to keep it in this form, then this is all right. But for solving a numerical problem, then it will be essential for us to give the numerical values of the length, the values of the moment of inertia, etc. Then this can solve. You will be able to give. Once you know beta, beta is equal to, we have used. Once we get beta, we know beta is equal to omega L by theta. So therefore, we will get infinite number of values of beta. So therefore, from this we will get a particular value of omega I is nothing but beta I by L into square root of So substituting the value of beta here, what we get from the transcendental equation will give us the corresponding frequency, and of course I will be 1, 2, 3. So this is just an example. So there can be another problem in which both sides of a shaft carry two disks, one with J1 moment of inertia, other side is J2, and the shaft dimensions are given, material is prescribed. We can find out again the equation for which, that means a transcendental equation we will get, and again solving which we will get ultimately the natural frequency. So thus we find that torsional vibration of shaft are very similar in its form and general form of solution also, and equation of motion also, as in the case of longitudinal vibration of parts. The next type of commonly used elements, machine elements we will find in machines will be beam. As you have mentioned, in case of beams, the direction of movement of the particles of the material object will be perpendicular to the longitudinal axis of the element. So next we take up, but by far that kind of vibration is far more common in machines and structures, and therefore we should take up that in more detail. It is true that longitudinal vibration of bars, etc. are important, but in reality what happens, we get most of the time lateral vibration of the structural members. So we come now to the transverse vibration of beam and such problems. Again, as mentioned earlier, we will take up uniform beams which are straight, and we represent this beam by this. Its longitudinal axis is x with the origin at one end as before. Now the displacement of the members or the elements will be in the transverse direction. So let us consider one particular element, and as we have been doing for the other cases, we will derive the equation of motion valid for this element. So this element comes at some time here, so that the face which is at a distance x from the origin is displaced by an amount u, and the face which is at a distance x plus dx is displaced little bit more than the previous one. Obviously it will be u plus del u del x into dx, where dx is the distance between the two ends of this element. Now if we consider the free body diagram of this element, the two ends, now when a beam bends like this, the moment acting here will be m, and bending moment, this is not twisting moment, This is bending moment. Bending moment in the other will be same as m plus, little different from this. Then we also know that during bending, this face will be subjected to a shear force, which is say V, and the other end will be also subjected to V plus del V. Now all these quantities V, M, U, they are all continuous functions of x, and of course at each point there is a value depending on that x and subject multiplied by a harmonic function of time, so that everything fluctuates harmonically with time with same frequency. Now let us now consider the relationships between various quantities. First of all, you see that the total moment we neglect rotary inertia. It means that in this direction rotation, first of all it is small vibration. So this u is very small, it hardly moves too much away from the original location, and the slope etc. are all very small, slope of the bending. So therefore the angular motion of the element is ignored. If this rotary inertia, rotary motion is ignored, then the total moment it is subjected to must be 0. Now what is the total moment? Now if we take the total moment in the anti-clockwise direction, it will be clockwise direction, it will be m minus anti-clockwise direction, which is m plus that is the moment in the anti-clockwise direction, plus there is a clockwise moment because of the two V's. This is slightly different from V, but nevertheless the total moment produced by two parallel and opposite forces will be V into dA. This behaves like a couple with arm length dA. This must be equal to 0 because there is no rotary inertia, and this gives us the shear force is minus shear force is equal to, we take it to the other side, that is the relationship we get. Fine. Now let us consider, still we have to get the relationship of these quantities in terms of the deflection. So we know that for bending theory, we know that beam equation says bending moment by second moment of area I is E by R, where M is the bending moment, I is the second moment of area of the cross section, is equal to E is the modulus of elasticity of the beam material, and R is the radius of curvature. Now if we see the radius of curvature in terms of displacement, how do we find out? So at one point here, for example, the slope is, if this displacement is in this direction, it is u. So del u del x is nothing but the slope of the tangent to a point, to that curve, which is nothing but the center line, this center line. So at this point we can find out the slope, and the slope will be tan inverse, because you know this tan of this angle is equal to del u del x. Now if we go to this point, this angle will be equal to tan inverse, what will be the slope? Del u del x, and here it is ready plus del 2u del x square dx, the slight difference. Now only thing we have to keep in mind that when we are taking this, if we represent this by, if we drop two perpendicular to two different locations, this angle will be the difference between the slope at this point and this, or amount of rotation of this, because this is also perpendicular to this is also perpendicular to this. So this is nothing but the difference in inclination of these two tangents, and that is given by simply this quantity. So since this is all small, so we call it del theta, and of course the two ends of the two elements are dx. So we know that r into delta theta is equal to dx. Delta theta we can replace by d theta. So now in terms of u, what we get here, that since these angles are all very small, we can always write tan theta is equal to theta. So therefore the difference between this and this will be, that d theta will be del 2u del x square into dx. Only thing we have to keep in mind that as x is increasing, slope is decreasing. So this is definitely a negative quantity, because if you go to increasing x, del u del x decreases. So therefore del pu del theta square must be a negative quantity. Now even if that you have to keep in mind, and finally we have to keep that there. So therefore we will get r del 2u del x square dx equal to d, or 1 by r equal to minus so we can write in this equation using, this is a standard equation, and now we have got another relationship. So using this in this, we get, or m is equal to minus ei del 2u del x square. Now for this is the positive definition of m. So therefore to maintain this sign equality, and this is always negative, that's why for positive m, del 2u del x square negative, so therefore this minus. Now so therefore, or v will be, now we know v is actually del m del x, so it will be minus Next we come to again as usual Newton's second law. So total force acting on this in the transverse direction is V plus del V del x dx minus V. So resultant force is only del V del x into dx. That is the force. And this must be equal to the acceleration of the element in the transverse direction multiplied by its mass. So it will mass will be A into dx is the volume into rho, that is the mass, and del to u del t square is the acceleration. So using this del v del x into dx, so therefore we get minus ei So therefore the equation we get now is del 4u, which is a function of x and t, del x4, or rather I should start from the other side, whatever it is. So this is the equation of motion for the element. Now it depends on modulus of elasticity, second moment of area, I, area of cross section, and the density, like this. So for normal mode oscillation, we can take obviously as before that this is composed of a function of x so when you substitute this here, you get minus x into omega square, cosine omega t gets cancelled from both sides, minus or the final form you can write like this. And the general solution what we can get, the if we take e to the power st form solution, then that gives us the characteristic equation as s to the power 4 is equal to beta to the power 4. So this tells us S equal to either plus minus beta or plus minus I beta. There are 4 roots: plus beta, minus beta, plus I beta, minus I beta. So therefore the solution will be of the form C1 e to the power beta x So therefore, the solution will have both hyperbolic terms and harmonic terms. This will lead to hyperbolic function, this will lead to harmonic function, or you can write like this: A cosine hyperbolic beta x plus B and the A, B, C, D, etc., including beta, will be determined by the boundary conditions. In case of beam, boundary conditions will be 4 in number, 2 ends. Each end you have to tell either the deflection and the slope. There will be 2 conditions. Or in the case where it is force is free, then shear force will be 0 and bending moment will be 0. We will take up this in the next presentation along with the solution of some problem.